Hello everyone, welcome back to the SWAM NPTEL course on engineering aspects of biofuels and biomass conversion technologies. I am Professor Ijaz Ahmed, currently Assistant Professor in the Department of Chemical Engineering at IIT Asim Dhanbad. In Module 12, which is also the last module of this course, we are discussing about non-edible oil and used cooking oil to chemicals production and fuel production. Particularly in lecture 1, we discussed about the introduction part. In lecture 2, we will discuss the non-edible oil properties and the processes. So if you remember here, in the previous class, we discussed about what we can do with the non-edible oil beyond the fuel. So we discussed about the biolubricants production, we discussed about the polymer precursors, we discussed about the oleochemicals, we discussed about the co-products, we discussed about the other application, for example, plasticizers, plastics, additives in grease, bioasphalt binder, cement additive, etc. If we discuss about the availability, like I said, the Jatropha is most common. If you see in India, Jatropha, Karanja, castor is also somewhat available, especially it is in Africa, but it is also available in India. We have neem available in India. So if you look at the major producing region, India, China, Brazil, and Indonesia are major producer of the Jatropha. But the challenge here is that Jatropha has a very long gestation period, and then there are toxicity concerns, yield variability. On the other hand, if we see the advantage, these are drought tolerant and can grow on marginally. Similarly, if I talk about the Karanja oil, it grows in the Karanja seeds you can get in India, Australia, Indonesia, but these also has long gestation period. Very limited large scale research has been done in this. But the best part is that it has nitrogen fixing capacity and high alkaline. The neem, everyone knows, in India it's very common. We brush our teeth also sometimes with the neem branches. So neem is available in India, Myanmar, Sri Lanka. Now the challenge here is it competes with pharmaceutical and pesticide use. You know, many of us uses the neem oil for wound healing and for several other reasons, especially our grandparents used to do that. If you get a wound or burn or something where you need an antiseptic cream, and if you don't have it, our grandparents used to use the neem oil for treatment. That means neem oil has a medicinal value and it is used in pharmaceutical and as a pesticide as well. Maybe if you will just Google out or you can look on your e-commerce shopping app, the natural pesticide for the plants in garden. You will see the neem oil will come as one of the options. So if we have to make fuel from the neem oil, then there will be a direct competition from the pharmaceutical and the pesticide use. But the best part here is that these are naturally pest resistant, thrive in varied soil types. Similarly, we have castor oil, which is produced in India, China, Brazil, and Russia. It doesn't mean that these are not found in other nations, but we are talking about in bulk. Where do you find it? So, India, China, Brazil, Russia, this has high viscosity oil, and as a result, it requires a special processing. But the best part is that it has very high oil yield and grows in diverse climates. Similarly, we have rubber seed, which is found in Malaysia, Indonesia, Thailand, and rubber seed is a seasonal seed, so you will not have available throughout the year. And also the oil produced from it degrades quickly after the seed fall. But the best part is that from the rubber, it's a byproduct of the rubber industry. And therefore we can make an integrated rubber production as well as the rubber seed derived fuel and chemical production unit as well. The other is we have Polanga. Polanga is also found in India, Indonesia, Malaysia, Sri Lanka. But these have very long gestation period again, very limited domestication. Seed may be toxic, but the best part is that it converts high oil content and can grow in salt and coastal region as well. That means we can grow it on shores also or the coastal areas also. Now If we talk about how do we extract the oil, so one is of course I said using the mechanical press. It has major advantages: higher yield, easy to operate. Like you have seen, if you have not seen that how we extract the oil from the mustard, how we get the mustard oil, so you must have seen these sugarcane juice sellers, right? What they do, they have a press like I showed you during the pelletization, that we have a press, two rolling press moving like this, and if you put anything and something comes in between, it will get pressed, and when it will get pressed, the oil will come out. So the most common extraction process is mechanical press, but which has very high yield and easy to operate. But the problem here is it requires high maintenance cost, continuous moisture reduction, refining, degumming, and it is not very good or ideal for the non-edible seeds. The other is solvent extraction, or we can say solvent extraction. It is low cost, easy to operate, causes higher yield, but the solvent toxicity, long term, high temperature, and solvent separation and refining are required. Some of the emerging technologies are like microwave extraction that enhances the yield, and less solvent is used, shorter extraction time is required because there is a direct heat transfer. There are no conventional and convection energy losses. Whatever energy you give, whatever heat you give, that goes directly and hit the compounds at molecular level. And because of that, the heating is very rapid, the thermal efficiency of heat transfer improves, and then that reduces the overall processing time. But the problem here is the operating temperature varies with solvent mode. And then controlling that again requires a controller which will have higher energy cost or higher capital cost as well. The other is enzymatic extraction, wherein we use organic solvent free environment. So here if you look at the Soxhlet apparatus, what we used, organic solvents, I told you earlier. Now enzymatic extraction, this is organic solvent free and more environment friendly, but the problem, it requires prolonged extraction time. Okay. Similarly, we have supercritical CO2 extraction, like I talked to you during the algal biomass conversion process. And therein we learned that supercritical extraction technology is used to extract the lipids from the algal biomass. So when oil has a similar kind of structure, we can always use supercritical extraction technology. It is green, it do not have any toxic solvent, doesn't require refining, it requires low temperature, and results in very high selectivity of the desired product. But the problem here is supercritical. I told you that it happens between 10 to 40 megapascal. That means you require a high capital cost instrument. Now, why there are several different methods for extraction of non-edible oil and why they are important. So, if we look at the physicochemical properties of non-edible oil because it comes from the different sources, different kind of oil plants like castor, mahua, karanja, all has different type of nature, different production cycle, and maybe some oil composition may vary. So we can say the non-edible oils vary significantly in viscosity, moisture content, acidity, and iodine number. And these parameters are very important because these influences their suitability for industrial application. For example, the viscosity affects the flow and handling. Flash and cloud point indicates storage safety and lower performance. If I talk about the acid value and FFA content, it determines the requirement for pretreatment before any downstream application. Similarly, we have iodine number, which refers to the presence of unsaturated fatty acids in the oil. Oil color that is coming from the non-edible sources is either yellow or dark brown or a color in between. Okay. If we look at the properties, for example, Jatropha, here we have Jatropha. It has viscosity at 40 degrees Celsius around 36 centipoise. The flash point is 292 degrees Celsius, cloud point is 2 degrees Celsius, iodine number is 135, acid value is around 1.5, free fatty acid content is 1.05, in color it is golden yellow. Then we have castor oil. Castor oil has a very high viscosity, 222, flash point is 294, cloud point is 14, iodine number is around 84, acid value is 2.41, free fatty acid is around 1.41%, it is also yellow in color. Then we have candle nut, which has a viscosity around 26, flash point not known, but iodine number is around 137, acid value is 1.59, free fatty acid is around 7%. The color is again golden yellow. But when we talk of Karanja, it has a viscosity of 40, flash point 225, cloud point 3.5, iodine number 87, acid value 5.7, and usually the free fatty acid content is 5%, but it is yellowish red in. So in case of Mahua oil, the viscosity is lesser, the flash point is 232, the cloud point is 15, iodine number is 71, acid value is around 36, free fatty acid content is very high, which is around 18%, the color is yellow. If I talk about Kusum, the viscosity is 25, flash point is 268, cloud point is 12, iodine number 215, acid value 21, free fatty acid content is 11%. Now for cotton, same, we have 29, 255, minus 3.5, it has a very good cloud point, minus 3.5. iodine number is 69, the acid value is around 0.24, the free fatty acid content is 1%. This is also yellow in color. Similarly, we can have neem, but neem, I would say that, see, neem has a very good pharmaceutical application. It has nutraceutical application as well for the topical formulations, like it has polyphenol and other antioxidants that helps to recover from the wound and the kind of some skin disease if we have. It also acts as an antibacterial, antimicrobial agent. So let's leave the neem. We have Polanga, which has a viscosity around 58, flash point is 239, cloud point is 8, the iodine number is 94, and acid value is 0.3. While free fatty acid content is one of the highest, which is around 22, and because of that it looks dark brown. Then we have rubber. It has viscosity 76, 198 flash point, 198 degrees Celsius, cloud point is minus 9 degrees Celsius, which makes it a very good oil. The iodine number is 135, acid value is 0.52, the free fatty acid content is 17%, and it is dark. If we look at that, what are the different acids which are present and why these colors are changing? So as I told you in the beginning, most of these compounds that we see are C16 to C20. Particularly here in, if you see, these are C16 to C18. We have palmitic acid, which is in Jatropha. If we see, we have maximum palmitic acid in Jatropha, or oleic acid is 44%, linoleic acid, and then palmitic acid. These three are the major constituent of the Jatropha oil, and then we have stearic acid. But if I take look at jojoba, there is no palmitic acid, stearic acid is only 4%, but oleic acid content is very high, linoleic content is very high. Similarly, we have candle nut, which has 6.23 palmitic acid, and then we have stearic acid. But if you look at the major component, 26 and 39% and 24%. Linolenic and linoleic acid, oleic acid are the major constituents. In Karanja, if you will see, 72% is oleic acid. So if we have to develop a technology, Karanja will be one of the easiest feedstock to convert, because its composition is not varying as much as like the other sources. 72% concentrated oleic acid is here in the feedstock, so you just have to separate. Then 11, approximately 12% is linoleic acid. Then we have Mahua. Mahua has like all these oleic acid, palmitic acid, linolenic acid, then we have stearic acid, so it has all. We have oleander oil, again palmitic acid, oleic acid, linoleic acid, etc. We have cotton oil, You can see the 50% it has linoleic acid. When I talk of neem oil, it has 62% oleic acid. If I talk about Polanga, the major constituents are oleic acid and linoleic acid. Similarly, for rubber, the major constituents are linolenic and oleic acid. For rice bran, the major constituent is oleic and linolenic. For tobacco, it is the maximum content is around linoleic acid, that is around C18. So herein, if I say that what we can make, so as I said, the first is that biodiesel. Now what we do here, the monoalkyl esters of long chain fatty acids are converted into the biodiesel via the transesterification reaction. The feedstock or this non-edible oil source can be, or the long chain fatty acid source can be oil, animal fat or vegetable oil. Now the non-edible oils have high free fatty acid and moisture. Therefore, the conventional technologies for conversion are very challenging. But still, the major conversion technologies are pyrolysis, microemulsification, transesterification. Now we are also doing cracking as well, catalytic cracking, and then upgradation as well. So these are new, some of the fancy terms, catalytic cracking or upgradation, that we can do for the non-renewable oil to convert into the fuel. Particularly if I talk about the pyrolysis, pyrolysis is a thermochemical process that uses heat to degrade the biomass under inert atmosphere. The temperature range is usually 300 to 800 degrees Celsius. When I was discussing about the pyrolysis, I said that one range is 350 to 550 degrees Celsius. Then there is other range greater than 700 degrees Celsius. Now, in both the conditions, the product composition will change depending on what temperature we have used, but usually we go for medium temperature range. The feedstock here we use are non-edible oils, animal fats, cellulosic biomass, and what we do is that we use a catalyst that reduces the activation energy barrier, and because of that, we get the reactions done at relatively lower temperature than the conventional pyrolysis process. The major product here are bio oil, or you can say pyrolytic oil, which is also a renewable fuel because it is coming from a renewable source. Now, this pyrolysis oil particularly is derived from the non-edible feedstock and can yield up to 67% oil from non-edible plant seeds. For example, for Mahua seed, there is a study that has been done by Pradhan et al. In a semi-batch reactor. The temperature range was around 450 degree to 600 degrees Celsius. And the maximum yield the researcher achieved was 58% at 525 degrees Celsius. Similarly, another case study by Shadangi and Mohanty that about the Niger seed. Now this Niger seed, what we do is that we use conventional thermal pyrolysis. We operate around 550 degrees Celsius and the oil yield we get is around 34.5%. Now for this what we require is a reactor. So the usual reactor that we have for pyrolysis are circulating fluidized bed reactor, bubbling fluidized bed reactor, focused solar reactor, rotating cone, ablative reactor. So I showed you that what happens, let's say when I have this reactor and there is some feedstock, usually we put it like a bed. But if I start giving gas from here and I keep increasing the velocity, this velocity, firstly it will go under, so let's say I write minimum fluidization velocity, so that would be Vm. If I further increase, what will happen, like you have seen the popcorn in the cinema halls, what happens, the guy who sells the popcorn, he pops it and the popcorn falls down from the top. That's a very good example of fluidized bed reactor. What happens when you increase the further gas velocity, the particles will start moving up, but because there is a gravitational pull, it will not go very high, so it will flow. If we increase further, So here we can say this is fluidization. If we increase further, it may form bubbles like this. This is called bubbling fluidization. If we further increase, then we can go to other kind of fluidization as well. So, and let's say because here we use catalyst, if we use a circulating thing, so catalyst regeneration unit and put it back here, that becomes a circulating fluidized bed system. Okay. The rotating cone ablative reactor we have already seen in during the pyrolysis. So we can say the pyrolysis is more or less similar. The only thing changing here is the feedstock, which is now in liquid state. As we know, the advantages for pyrolysis are they are very easy to handle, store and transport. Should have ideally high Seton number, low viscosity and low sulfur content. Problem is that this pyrolysis oil is mostly acidic in nature and has high content of moisture. It's a mixed hydrocarbon compound, denser, usually denser than the petroleum diesel, and therefore it requires pre-treatment, for example, neutralization and dry. Now the other technology I said after the pyrolysis is microemulsification. So in microemulsification, what we do is we formulate the hybrid diesel fuels. Actually, we do emulsification to reduce the viscosity with using a suitable emulsifying agent. For example, primary alcohol. Now that produces thermodynamically stable microemulsions. It's a single phase, translucent, stable at constant pressure and temperature. Now, it must be noted that the surfactants also improve the emulsion stability. For example, SPEN 80, which is a hydrophobic surfactant, has been reported to improve the emulsion stability because of its, like, when emulsion is formed, there are hydrophilic and hydrophobic interactions that happens. For example, the Liang et al. Stabilized the bioil in diesel with SPEN 80 or Twin 80. These two are the surfactants. Similarly, Sankungom et al. Produced the microemulsion biofuel from the Jatropha carcass. Now, if we look at the properties of the fuel that we get after the microemulsification, kinematic viscosity, the heating value and moisture content of this microemulsified fuel meets the biodiesel standards, and therefore it is very compatible with the diesel engines. The advantage here is, of course, low energy consumptions. There is no need for pre-treatment, unlike cracking, blending or hydrodeoxygenation where you require the pre-treatment. It reduces the viscosity and free fatty acid content in the non-edible oil, reduces toxic pollutant emissions, improves combustion performance, lowers the ignition delay. Fuel properties are very close to petrol and diesel. The higher oxidative stability, it has higher oxidative stability than petrol and diesel. But the limitations are that it may lead to incomplete combustion or carbon deposition in the engine. Now, the third technology is transesterification of non-edible feedstock. So, what do? Most widely, we use this transesterification to produce the biodiesel, particularly from either its algal biomass or from the fat or the non-edible oil. The problem is that what we get is a high viscosity biodiesel with some free fatty acid and the moisture. Now, this transesterification reduces the viscosity, free fatty acid and moisture, and therefore it produces the biodiesel with improved fuel property. The advantages herein are, of course, the process is eco-friendly, requires mild reaction conditions, and it is suitable for wide range of biodiesel feedstock. So this is all for today's class. See you in the next class. Thank you.